this section I will make a comparison between the traditional approach and the Bayesian approach to model comparison. So let's recap the Bayes theorem. Bayes theorem has 4 components. This is the prior, this is the typically called likelihood, the probability of the data, and the posterior. So the prior in this case is a prior probability over parameter values. So the parameter of interest is theta. The Greek letter theta is used as a generic term for any type of parameter. It could be the mean of a population, the mean differences in a population, the regression coefficient in a population, a proportion in a population, etc., etc., etc. So this is the prior, that the probability distribution we have to establish our credence, the credence that we give to possible parameter values of that parameter. And here is the probability of the data given the parameter value. So for a parameter value, let's say a mean of 0, then what's the probability of observing the data we obtained in our study, which is the mean of our sample, for example. Probability of the data is very complex when we have complex models, and we have to calculate for all possible values of theta and multiply that probability by this probability, and then the sum of all that. But if it is a continuous variable, then it would be the integral of that. That would be the probability of the data. So quite complex. Sometimes we cannot calculate, and we use approximations or simulations to approximate to that value. And then when we have all these 3 components, when we just obtain the ratio, and we get the posterior probability, which is a distribution over the parameter value, same as here, same as the prior, but it's after observing the data we observed in our study. Now we are going to make a change to this generic form of the theorem, and then we are going to give it a meaning using the example we've been used in the linear model. So the parameter value that the parameter we are interested in is beta 1. So the beta 1 coefficient in a linear model. And here we are going to have a distribution over different possible values of beta 1. And here in the probability of the data, given the parameter, so for each possible value of beta 1, we have to determine what's the probability of obtaining the B1 that we obtain in our sample. And we obtain that this is equivalent to a sampling distribution. And then what's the probability of obtaining B1, the one that we obtain in our sample, would be the integral of these two components. And when we obtain the ratio, that's the posterior distribution. So it will be our new credence that we give to different possible values of beta 1 after observing the B1 that we calculated in our sample. Now let's see things that the first element that I want to direct our attention is the probability of the data given the parameter, because this is something that the traditional method and the Bayesian method share. So in the traditional method, the probability of data given the parameter is the sampling distribution for B1. And we want to know what is the probability of obtaining different values of B1 from a population in which beta 1 is 0. or in more formally, probability of B1 given that beta 1 equals 0. What do we do in the Bayesian? In the Bayesian method, we do the same, sampling distribution for B1, and we want to know what is the probability of obtaining different values of B1 from a population in which beta 1 is unknown. So basically, the difference is that in the traditional method, beta 1 is fixed to 0, so we only allowed one value for beta 1, whereas in the Bayesian case, we allowed beta 1 to take a range of possible values. So, what about this probability? Well, we give a bit more information. We say that B1 is normally distributed with mean 0, and standard deviation is the standard error of B1, which there is a formula to calculate, but we are not going to go through that in here. And for the Bayesian method, exactly the same, with the difference that the mean will be different values. So we are going to have different possibilities for beta 1, not just beta 1 equals 0. So this method is applied only to the model of the null hypothesis, because we are going to have a model of the null hypothesis and a model of the alternative hypothesis in the Bayesian case, but we are going to have only a model of a null hypothesis in the traditional case. Okay, so a way of representing the probability of the data given parameter in the traditional method, we've got that this is the sampling distribution of B1, and the mean of that distribution is beta 1, which is 0. Okay, whereas in the Bayesian case, we've got a range of possible values for beta 1, and so we've got multiple distributions, multiple normal distributions, with the mean in each case is a different value of beta 1. Here I give a better attempt to represent graphically the probability of data given parameter that I showed before. So the previous attempt is a bit clumsy because I'm presenting several small normal distributions when in fact is a continuous space. So if you see here, then we've got a better way of presenting the normal distribution. Instead of using multiple curves, we use color. So color, the black would show that the probability is at the highest of the distribution, and then it goes down and down to the side. So blue is almost 0, and then this white is close to 0, and this orange a bit more, and browns a bit more, and black is the highest probability. So it's that the range of probabilities is represented in this column. So, as I mentioned before, for each possible parameter value of beta 1, and here I'm being very generous and I'm including values from -500 to 500, we have a normal distribution. So for 0, we've got a normal distribution which tells us what is the probability of obtaining different different B1s in the sample. And well, if the parameter beta 1 is 0 in the population, well, the B1 in the sample can take this range of values. The most likely, of course, is 0, but values close to 0 are also likely, but you go further away from 0 are less likely, and further away it's 0 or almost 0. Okay, and we do the same for each possible parameter value. The difference with the traditional method is that here we do this for only one value, the value of 0. So we assume that beta 1 is 0, and we want to know what's the probability of obtaining different B1s in the sample. And that's given by the colors in this vertical line. Okay, so let's go to the prior probability. So we explore the probability of the data given the parameter values. Now let's explore the prior probability. So in the prior distribution for the traditional model, we say that for the null hypothesis that beta 1 equals 0. So no other value is possible. In the prior distribution, in the Bayesian model, for the null hypothesis model, we actually say the same, but we use the probability language to say that. We say that the probability density of beta 1 being 0 is infinity. So basically, we say that that's the only possible value. And probability of beta 1 being different than 0, we say 0. So other values are impossible, which is the same as saying that, but in a different language. Now, for the alternative hypothesis in the traditional approach, we just say that beta 1 is different than 0. Some alternative hypotheses are that beta 1 is more than 0 or that beta 1 is less than 0, so they are directional hypotheses. But in this case, we just say that it's different, could be higher or lower. Now, for the alternative hypotheses, we put a distribution over possible values. And these are three options that we can use, and there are many others. But these ones are what they are called a default priors, which try to give very little information about the parameter values. So they don't want to influence the current data. So we assume almost ignorance on what are the possible values for beta 1, and we let the data tells us what we should do about beta 1. So in this case, we say that beta 1 is normally distributed with a mean of 0 and a standard deviation 0.7. So basically, this is a normal distribution, and values close to 0 are more probable, and further away from 0 are less probable. We can use JASP uses this one, which is a Cauchy distribution with R parameter being 0.354, and which has similarities to the normal. So this shape is similar. And another option is to put a uniform distribution that from an interval that goes from negative infinity to infinity, so all the values are equally likely. Okay, so this is a way of demonstrating graphically these distributions. So for the traditional, the null hypothesis, a spike on 0 for possible values of beta 1. And the same for the prior of the null hypothesis. We put a spike on 0. For alternative hypotheses in the traditional approach, we don't provide a distribution. So we vaguely say that beta 1 is different than 0, but we don't provide a distribution. What possible values are for beta 1? How probable are each value? We don't say. In the Bayesian approach, we do define that, and we use a Cauchy or a normal distribution, or it could be uniform. Here it's a normal distribution. Okay, so let's go to combining the prior probability with the likelihood. And that would be to add the sampling distribution that we showed before with the prior. So we are multiplying the values on this curve times the values in here. Now, because this distribution only allows a parameter 0 to have some probability, all the other parameter values are impossible, then it will not change anything. The values that were here before, they will remain. For the null hypothesis in the Bayesian approach, it's exactly the same. So we defined these distributions as I showed in color in the previous slide, but because in the prior we are saying that values different than 0 have a probability of 0, then when you multiply 0 times those probabilities, you obtain 0. So all the values here and there will be 0. We can only have values of probability values there in 0, and they will take the values of the probability distribution here. In terms of the alternative hypotheses, we've got we combine these sampling distributions, which are the same as in this case, but now they are not multiplying by 0. They multiply by the values of the probability distribution here. So these values times these values will be quite small values, but when we go close to the center of the distribution, these probability values, these ones will be less small. And by combining these two things, we have an approximation to the prior distribution. Sorry, an approximation to the posterior distribution. Now, we need to go to the probability of the data. This is quite difficult to calculate when the models are complex and with continuous variables, like in this case. Okay, so in the traditional approach, the probability of the observed data for the null hypothesis, that's a probability of B1 equals the probability of B1 given that beta 1 equals 0. That's exactly the values that we obtain in the sampling distribution. In that distribution, how likely is to, or what's the probability of obtaining the B1 we observed in our sample? And that's the probability of the data. The same for the null model in the Bayesian approach. The probability of B1 will be the probability of B1 given that beta 1 is 0. And so we use the values of that sampling distribution. What's the probability in that sampling distribution of observing the value of B1 we observed in our sample? In the alternative hypothesis, this is not calculated, but in the Bayesian approach, we do calculate that. Probability of B1, now it's an integral of the probabilities of B1 given all the beta 1s. So for each beta 1, we obtain what was the probability of observing the B1 we observed in our sample, and we integrate all these values to obtain that probability. Okay, graphically, that's my best attempt to show this graphically. So in the traditional approach, we've got the sampling distribution only at value 0, and let's say we observe some data. The mean in our population, the mean in our sample is 200. So this line indicates that we observe 200. So here, where the value 0, parameter value 0, and the number 200 intersect, and this is a probability value which is in the blue area, that means it's a very, very small value. So because we don't have to add any of these values, remember these values will be are not considered in the values that are not zero for the parameter values are not considered, so we can only look at that. So when we add those values, we have only one value to add. So the probability of the data here, it will be this probability over there. And the same applies for the null hypothesis. So the probability of the observed B1, which is 200, is here, is this value. But here, this graph is a bit more complicated. What I did here is to present the prior as a normal distribution, but with color instead of a curve. So that's what is showing here. It's a prior distribution over parameter values. And we multiply the values of this probability distribution by the values that were here in the previous, that are shown here. And by that multiplication, we observe this. So that is the combination. Probability of B1 given beta 1 times probability of beta 1 is this. So you can see that we had values in brown here, and we only got to the values in white. So very, very small values indeed. And the green line here shows the B1 that we obtained in our study, and what we have to do is to add all these values here, and that will give us a value there, which is the sum of all these, but it's actually an integration rather than a sum. Now you may say, but if they are all blue, well, they are blue, but remember that I said blue is almost zero, it's not exactly zero. So you're adding loads of numbers there that are small, but adding a lot of small numbers, you get some number that is a bit higher. Still not great, but still more higher. So for this model, the probability of obtaining the data we observed, which was a 200, is given by this value.